Hi folks, welcome to week 5 of physics. We are going to be working through energy, potential energy, kinetic energy, and then conservation of energy. If you have a packet of notes, we are on the purple sheet of paper. Otherwise, under the week 5 folder, you will just need to pull it into Schoology. So up at the top, the energy notes, the actual definition that we're going to be using for energy is the ability to do work. So if you remember from last week, work is applying a force, a push or a pull, over a distance. So if you push something through a distance, you have done work. In order to do that, you needed energy. We're going to look at two types of energy. The first one is kinetic energy. Kinetic means motion. So that is the energy of motion. And it will be measured in joules, just like work was last week. So work and energy are both measured in joules. Power was in watts. In order to calculate kinetic energy, we abbreviate it with a KE. So KE, it is on your equation sheet, right under work and energy. If you look all the way over to the right side, KE stands for kinetic energy. It is 1/2 times the mass times the velocity of the object squared. You have to have velocity to be in motion in order to have kinetic energy. M stands for mass. It has to be in a kilogram. And then V stands for velocity. It does have to be in meters per second. So you will have to convert it from miles per hour to meters per second before you plug it in there. If you wanted to find the kinetic energy of a kid with a mass of 46 kilograms, if they were traveling at 8 meters per second, kinetic energy is 1/2 times your mass, which is 46, times your velocity, which was 8 meters per second, squared. When you take 1/2 times 46 times 8, I got approximately, and you can round differently, 1,472, and then the units for both types of energy are going to be a joule. Right here, the units of kinetic energy. People will ask, it doesn't make a lot of sense. We've got a kilogram, and then we have a meter per second that gets squared. How does that turn into a joule? Think of it like a math proof. This is just for the people that are interested in it. Why does it turn in, all these weird things turn into a joule? If you remember from last week, a joule is the same thing as a Newton times a meter, because it was force times distance. So when we took work equals force times distance, a joule was the same thing as a Newton meter. We know from before, a Newton is the same thing as a kilogram times a meter per second squared. A Newton measures force. You take mass times acceleration. So really what a joule is symbolizing is all of those weird things in there together. So if you look at the units for this, you have a kilogram times a meter squared over a second squared, because both of them get squared. Inside of here, you have a Newton, a kilogram times a meter per second squared, and then there's one extra meter. So if you pull out that to a meter, and then you have one left over meter, a Newton meter is the same thing as a joule. Okay, if that didn't make sense, you can ignore it. I just wanted people that were curious to kind of be able to see what was happening to the units in order to turn it into a joule. Okay, the second type of energy that we are going to be looking at is potential energy, or gravitational potential energy. And potential energy is energy that has been stored. And you can have different types of potential energy. Like food is a potential energy. It stores it until your body burns it. But we are not going to be concerned about that. We are going to only look at gravitational potential energy. So things that are lifted up to a height. So stored energy due to height or position. It is also measured in a joule. All energy is measured in joules. In order to calculate potential energy, it is abbreviated with a PE. So on your equation sheet, when you're looking for potential energy, you gotta look for PE. It is mass times gravity times height. Mass still has to be in kilograms. Gravity is still -9.8, and it's meters per second squared. And then H stands for height. I don't know why they have to make this difficult. We have been using Y, delta Y for the vertical distance, the change in height the entire year. Potential energy, they change it. Instead of just calling it delta Y, they call it H for height. But it is still the same thing. It is measured in meters. Okay, once again, just to kind of show you where the joules come from, when you're taking all of these things together and multiplying them by each other, it turns into a joule. Because we've got a kilogram from the mass, we have times a meter per second squared, times the gravity, the acceleration, and then we times that by another meter when you add in the height. This right here is equal to a Newton. We have one leftover meter, and a Newton meter is the same thing as a joule. Okay, so once again, you don't have to memorize that, but it's there for those of you who are curious of why do those things turn into a joule. The other thing to kind of keep in mind, and I am going to circle it or box it in, the potential energy will always come out positive because the negative sign on the height, remember anything that's going to move downward gets a negative sign on its height, and the negative sign of gravity, negative 9.8, they are going to cancel each other out. So right now you can make a decision. You can just completely ignore all the negative signs for any time you're calculating potential energy, or if you can make your gravity and height are both negative, which is what I'll do just so I don't confuse people. When have two negatives, they cancel out and you're left with a positive. Okay, so for example, when you are calculating the potential energy of a kid with a mass of 46 kilograms standing on a ledge 1.5 meters above the ground, calculate his potential energy. So potential energy is mass times gravity times height. The mass was 46 kilograms. Gravity is negative 9.8. And the height is 1.5. But technically, because it's standing up and they're going to go downward through that height, it is a negative. Okay, these two negatives cancel each other out, so you end up with a positive answer. Once again, that is the way that I will do it. I'll make both of them negative because that's what we're used to doing, but if you just want to ignore the negative signs and not include them for this unit only, you can do that. When you multiply the three of them together, 46 times negative 9.8 times negative 1.5, I get like 676.2, and all energy is measured in joules. All right, so kinetic energy, the energy of motion, you have to be moving to have kinetic energy, 1/2 mass times velocity squared. Potential energy, gravitational potential energy, it is stored energy because of a height or a position, so you are lifted off the ground. In order to calculate that type of potential energy, you need to take mass times gravity times height. All right, our last piece, the conservation of energy. This is real similar. If you think back to chemistry and your conservation of mass, what that stated is whatever chemicals you put into a reaction, the same amount of atoms had to come out of it, but they can rearrange themselves. That's what a conservation of energy states. It means that as energy transfers from one thing to another, the energy is not lost. It doesn't disappear. It is just transferred, or in other words, converted from one form to another. Okay, so if you are riding on a roller coaster and you are way up here on the top and you're about to go down this hill, up at that very, very top you have a ton of potential energy because you have a lot of height. Okay, you sit there and you slowly inch over. You have a lot of potential energy, but you're not moving very fast. So you have a low level of kinetic energy. Then you start to go over the hill. As you fall down, you are losing potential energy because you're losing height, but you are gaining kinetic energy because you're moving faster. When you finally get all the way down to the ground, you're going as fast as you will. You have a ton of kinetic energy. The potential energy goes down to zero because you have no more height. It transfers between the two types of them. We are going to assume we don't lose any of it to friction or to heat. It just gets converted from one form to the other. All right, what that states is the total starting energy has to equal the total ending. So whatever you have at the beginning has to be equal to what you have at the end. So at the top of the roller coaster hill, if you add up all the energy, it has to be equal to how much energy if you add them all up at the bottom of the hill. You can't lose any of it along the way. Okay, so in order for that to happen, the initial potential energy plus the initial kinetic energy, all the energy you have to start initially, has to equal the final potential energy plus the final kinetic energy. All the energy added up at the end. They have to be equivalent to each other. All right, from there, we can actually take their equations. What is potential energy equal to? And we can plug it in. We then just have to add I's and F's to represent, is it at the beginning, initial, or is it at the end, final. So potential energy is mass times gravity times height, initially, plus initial kinetic energy, 1/2 mvi squared. That has to equal potential energy at the end, mghf, final height, plus kinetic energy at the end, 1/2 mass times the velocity squared. Okay? The nice thing about this equation is, if you look in every single chunk, there is a mass. If a mass is multiplied by, it's in every single one of them, you can cancel it out. So this equation gets cut down, all the masses get canceled out. All right, so without the mass, we have gravity times the initial height plus 1/2 of the vi squared, the initial velocity squared. And we set that equal to g times hf, gravity times the final height, plus 1/2 vf squared. So it's just the same equation from up above, we've just canceled out all of the m's. You cannot cancel out anything else. Notice, not everything has gravity, not everything has height, not everything has velocity. The rest of the stuff has to stay. All right, how do we use this equation? So as we work our way through, once we plug in numbers to our conservation of energy, we will use that equation to solve for an unknown. So as you look for the example, Adam, let's say he has a mass of 65 kilograms, goes sledding. Find his speed, his velocity, at the top of the second hill. So as you look at my drawing, right here at the initial point, he is at a height of 15 meters. HI is going to be 15. Technically, it's going to be a negative. You can either drop out all the negative signs, or you need to put a negative sign in front of your heights, because then it'll cancel out the negative sign in front of gravity. All right, the initial velocity of your sled, if you're sitting on your sled and you haven't started yet, your initial velocity is equal to 0. You're then going to go down and back up. It's a weird shape. We don't have a great equation for that. That's what conservation of energy helps us find. At our second hill, we can find the velocity right there, knowing that we're at a height of 5 meters. Technically, because it's going to move downward from there, it's a negative 5 meters. And our VF, our final velocity at the top of that hill, that's what we're solving for. Okay, so I'm just going to rewrite that equation right there. GHI plus 1/2 VI squared equals GHF plus 1/2 VF squared. All right, first thing, get rid of anything that's a 0. The initial velocity is 0. This whole chunk right there cancels out. Whenever you have a 0, it's going to cancel out that whole chunk. Okay, so we're now down to GHI equals GHF plus 1/2 VF squared. All right, I am ready to plug in the numbers that I have. Gravity, negative 9.8, times my initial height, negative 15. Either make them both negative or both positive. Think of it like an absolute value, it will cancel out. That is equal to gravity, negative 9.8, times HF, that is a negative 5. Once again, the two negatives are going to cancel out, and then what we do not know is the VF. So we are going to have that 1/2 VF squared. We are going to solve for the final velocity. All right, first thing you do, get yourself some numbers. If you take a negative 9.8 times a negative 15, I got 147. On the other side of the equal sign, if I take a negative 9.8 times a negative 5, I get 49 plus 1/2 VF squared. Don't know what VF is, that's what I'm solving for. Okay, in order to do the math on this, you have to first subtract, then divide, then square root. So it's kind of 3 steps along the way. So the first thing I'm going to do, I'm going to subtract 49 from both sides. When I do that, I get 98. And over on this other side, this cancels. So on the right side, all I have left is 1/2 VF squared. Okay, from here, I need to divide by 1/2. Don't divide by 2. You got to divide by 1/2 or 0.5. So both sides, I got to divide by 1/2. It cancels out. 98 divided by 1/2, it gets bigger. It is 196. That is still not VF. That is VF squared. My last step to find the final velocity, I need to square root both sides, and I get a final answer of 14 meters per second. All right, I did leave on accident one little piece right here. This was what I was talking about before, like on the roller coaster. If you start from a height, you have a lot of potential energy. The kinetic energy, if you're not moving, you're on top of a diving board, let's say, you're about to jump off, but you're not moving yet. If you're not moving, you have no kinetic energy. If you dive into the water at the very bottom, you have no height, which means you have no potential energy. You could calculate your kinetic energy, or you could know that whatever you start with right here, these add up to 100, that's what you have to end with as well. Okay? If you are halfway, half of the potential energy has been changed over to kinetic energy. It has to be 50-50 at the halfway point. You have lost half your height, so you have half the kinetic energy, and you have, half the potential energy, and you have gained velocity. You're getting faster, so you have gained kinetic energy. They have to add up to the total of 100 as well. Okay, so just to quickly recap, kinetic energy is the energy of motion. It is equal to 1/2 times the mass times the velocity squared. If you do anything wrong, people forget to square that velocity, so just double check that. To calculate potential energy, that is the energy stored due to height or position. You have to be off the ground. You take mass times gravity times height, cancel out all those negative signs, make sure that it turns out to be positive. And then finally, conservation of energy. When something transfers energy, it does not lose it along the way. It just transforms or transfers or converts it from one form to another. So all of the energy at the beginning has to equal all the energy at the end. We have a special equation. You will find this on your pink equation sheet right over here. We have PE, potential energy, KE, kinetic energy. Conservation of energy has that, and that, but I have boxed it in. This is the one we want to use. Either one of them will give you the same answer, but you have 4 chances more math to make a mistake at if you include the mass. It'll give you the same answer, but this one is an easier equation to work with. All right, you can use that to find a height, initial, a final height, an initial velocity, or a final velocity of things that don't necessarily move kind of in straight lines like we had been doing. So, all right, that is it for the energy notes. I will see you on Zoom this week.